In this video, we'll present our work, Label Leakage and Protection in Two-Party Split Learning, that was completed at ByteDance. Prior work has shown that raw data can be leaked through communicated gradients in horizontal federated learning. In our work, we show that data leakage can also happen in vertical federated learning, where data is partitioned according to features instead of different devices. Specifically, we first identify that in a realistic two-party split learning problem setting, one party can uncover the other party's private label information using the communicated gradients. To protect the participating party's private label data, we then propose a theoretically justified random gradient perturbation method that strategically calculates how much noise should be applied. To motivate our problem setup, we first discuss a real-world setting for split learning. Here, we have two parties where the first party is an online media platform and the second party is an e-commerce company that displays advertisements on the media platform. A user on the platform will periodically be shown advertisements from the e-commerce company. If the user clicks on the ad, he or she will then be directed to the product page of the e-commerce website, over which he or she can then decide whether to make a purchase. For this same user, the two parties have different features. The media platform has the features of the user's interest and viewing history, while the advertiser has the binary label of whether a purchase is made or not. In many real-world scenarios, the advertiser is unwilling to share its users' purchase information with the media platform due to privacy and business secret considerations. As a result, for both parties to jointly learn a model that predicts users' purchase behavior, we can formulate this as a two-party split learning problem. The main question that we study in this work is whether the label information can still be leaked in the split learning setting where no raw data is communicated. To abstract the previous example, we consider the two-party split learning problem, where the passive party on the left and the active party on the right want to jointly learn a model for a binary classification problem. For every training example pair x, y, the input feature x is stored on the passive party side, while the binary label y is stored on the active party side. Here, the model is represented as a function composition h of f. The passive party wants to learn a representation function f that maps an example's feature x to a vector representation in Rd, while the active party wants to learn a prediction function h that takes the representation computed by the passive party and return the positive class logit lowercase l. Here, the representation f of x is communicated from the passive party to the active party before h is applied. With the logit l, the predicted probability of the positive class tilde p1 is calculated through the sigmoid function, and the entire model h of f incurs a cross-entropy loss of capital L with the correct label y. To train the entire model h of f using gradient descent, the active party starts the gradient computation from the cross-entropy loss and compute the gradient with respect to the logit. The scalar derivative is equal to the difference between the predicted probability of the positive class and the actual label. Then, using chain rule, the active party can propagate the gradient to h's parameter. In order to also update function f's parameters on the passive party side, the active party also needs to compute a gradient of the loss L with respect to the representation vector f of x. We denote this representation's gradient by g. The active party needs to communicate this gradient g back to the passive party. After receiving g from the active party, the passive party can then keep backpropagating and update f's parameters. If we look at the form of the communicated gradient g, we'll see that by chain rule, it is a function of the active party's label y. Thus, a natural question to ask is if this communicated gradient will leak the active party's private label. To answer this question, we give a simple way that can uncover the label y for many practical two-party split learning applications. Here, we look at the 2-norm of the communicated gradient g. For many real-world datasets in online advertising or healthcare applications, at different iterations throughout training, the absolute value of p1 minus y is consistently larger for the positive examples than the negative examples, as shown in the figure on the left. This is specifically due to the fact that the learned model is in general less confident about a positive example being positive than the negative example being negative. On the other hand, as we see in the middle figure here, For both the positive and negative examples, the 2 norm of the gradient vector of h is roughly of the same magnitude. As a result, the communicated gradient g's 2 norm, which is the product of these two terms, is generally higher for the positive examples than the negative examples, as shown in the right figure. Thus, by looking at g's 2 norm, the passive party can very accurately figure out the corresponding example's hidden label stored on the active party side. More concretely, using g's 2 norm to predict the label y has an AUC of higher than 0.9 throughout training. This shows that the active party's labels are significantly compromised. Because of this possibility of label leakage through gradient computation, the active party should aim to send the essential information of the gradient without actually communicating its true value directly. In our work, we achieved it through random perturbation. Before sending the gradient g, the active party will now randomly perturb it and send the perturbed gradient g tilde to the passive party. Here, by linearity of expectation, as long as the random perturbation is unbiased, the computed gradient for F's parameter will also be unbiased. Thus, we naturally consider adding zero mean Gaussian noise as perturbation. Because the positive and negative examples have very different gradient distribution, as seen from the 2 norm analysis, we consider using Gaussian noise with different covariance matrices sigma 1 and sigma 0 to be added to the positive and negative examples gradients respectively. We denote the gradient distribution of the positive and negative class by p tilde 1 and p tilde 0. Additionally, for the training loss to be optimized efficiently, we also want the random perturbation's variance to be as low as possible while achieving the same level of protection. Thus here, we need a formal notion of label protection quality. Here we consider a general class of labeling functions where each function I sub a is the indicator function of the corresponding set A. We think of each of these functions as a classification rule that guesses an example's label to be 1 whenever the example's communicated gradient g is in the set A. This general class of labeling functions would contain the 2 norm method that we identified previously when we let the set A to be the set of vectors with 2 norm greater than some threshold t. With this class of functions defined, our goal is to perturb the gradient so that none of these functions is able to guess the unseen label accurately enough. For specific labeling function I sub a, we measure its performance in guessing the label by the detection error, which we define to be the average of the false negative rate and the false positive rate. Here, the false negative rate refers to how frequently the labeling function would wrongly think that the perturbed positive gradient g comes from a negative example, and the false positive rate is exactly the opposite. To protect against this entire class of labeling functions, we focus on the function that guesses the labels most correctly among this class, which by our definition is the function that has the lowest detection error. This lowest detection error is exactly equal to a value involving the total variation distance between the perturbed positive and negative gradient distributions. This is specifically by the definition of total variation distance. To guard against this worst-case labeling function, the active party would want to maximize this worst-case detection error. To do so is equivalent to choosing the noise variable's covariance matrix so that the total variation distance between the perturbed gradient distributions is minimized. However, directly solving this unconstrained problem will result in adding infinite amount of noise to the communicated gradient. Thus, to allow the training optimization to proceed successfully, we add a power constraint. The constraint upper bound capital P controls the amount of added variance and is a tunable hyperparameter to trade off between protection quality and learning performance. Because the total variation distance between high-dimensional distributions are analytically intractable, we instead minimize the symmetrized KL divergence upper bound of the TV distance. With some additional constraints and assumptions, we can solve this optimization exactly very efficiently. After getting the optimal covariance matrices, the active party can then sample from the corresponding Gaussian distribution and add it to the gradient g before communication. Experimentally, we find that our approach can successfully defend the two-norm label uncovering methods described before by achieving a much lower leak AUC of around 0.5 instead of 0.9. Additionally, by varying the constraint constant p, our approach can flexibly trade off between the amount of privacy protection and the learned model's test performance. We also show that due to the strategic perturbation, our approach can achieve better privacy versus performance trade-off than other naive protection baselines, such as adding isotropic Gaussian noise. Please check our paper on arXiv if you're interested, and contact us if you have any questions. Thanks.